Okay, we're starting. Last time we started 11.2, which was series. And now we're going to pick up with that. So we kind of know what a series is, what it means for a series to converge. Finite series are no problems, you just add them up with a calculator or a computer. It's when you get to infinite series, that's when things start to get strange. And you need to figure out ways of approximating them, ways of knowing if they have some sort of meaningful answer, because you can't actually add up an infinite number of things. A computer can't actually add up an infinite number of things. So we have to get to the answer in a more sophisticated way. And so, one, we define what it means to have a meaningful answer. So we look at the partial sums, look at them as a sequence, and if that sequence converges, we say, okay, the sum of these infinite terms actually converges as well to whatever that limit was. So that's great in theory. In practice, this is insanely difficult to actually implement. So a lot of times, we won't be able to find such a sequence to take the limit. Sometimes we might find the sequence and the limit is hard to take, but a lot of times we won't even be able to come up with that sequence in the first place because the function that we're looking at is so complicated. And so sort of the best we can do is sort of, one, know that it should converge to something based on some other test, and two, we can approximate what the series would converge to. Usually to any degree of accuracy we want, so we just make a choice. Okay, I just want to be right up to 10 decimal places. I don't care about being infinitely accurate. And so you can actually get the answer to that, which we'll deal with later. But for now, we're really going to concern ourselves with what we call the series tests. So this is from like 11.3 to 11.7. The convergence tests for series. And the goal of these sections, we're going to do it all at once because it's really summarized in that table I gave you. And the goal here is to know if a series, of course usually the infinite series because the finite series always converge, right? You just add up the numbers and you get it. Know if a series converges without necessarily knowing what they converge to, or the sequence of partial sums. So there are times when the thing you're looking at is too complicated, you can't know what it will converge to. It's also hard to find the sequence of partial sums. But knowing that an answer exists is important because then you can start working on approximating that answer. And so that's what these convergent tests are. They will basically tell you for a series that you're given, is there an answer out there? Will this converge, or are you just wasting your time? They will also tell you, does the series converge conditionally or absolutely, which we mentioned last time. And absolutely just means if you put all the terms in absolute values, the series converges. And if you remove the absolute values, then it diverges. That's called conditional convergence. And the importance there is that absolutely convergent series, you can rearrange the terms in the sum and it won't change the answer. But for conditionally convergent series, rearranging the terms will change the answer. In fact, you can change the answer to literally whatever number you want. And so that's going to be important. But our focus for today is figuring out when these tests actually converge. Is there an answer? Is there something worth looking for? Is there something worth approximating? Or should we just, it diverges and we just not worry about it? So that's what the goal is here. One series is easy though. Right? There are a couple. Like if you have a telescoping series, we actually showed how to actually find exactly what that converges to. Another one is sort of easy as well. This is the geometric series. Alright, so this is your A, R not equals 0 because it would be silly otherwise, and it has the form n goes from 0 to infinity of A, R to the n, or 1 to infinity of A, R to the n minus 1. These are of course equivalent, but you might want the subscript to start at a certain value for theoretical purposes. but that's basically it. So basically it's just a sum that has this form. It's one number, and you keep multiplying that number by some other number over and over and over. Right? And if you add up all these terms, you get what you call a geometric series. Now it turns out, these guys, we actually can know what the answer is, and it's not that hard. So first of all, notice that if r equals 1, we diverge by test for divergence. So assume your r is not 1, right? If I just plug in r equals 1, then that's just the sum of a plus a plus a plus a plus a for infinity, and my a is non-zero, so the limit is non-zero. So I'm just keeping adding stuff that's non-zero. It will diverge to infinity. So let's assume our r is not 1, and let's try to actually figure out an answer here. It turns out we can write, you'll notice that if I look at S1, I can look at that as, say, a, and S2 would be a plus ar, S3 would be a plus ar plus ar squared. S4 would be, let me look at the first term as the 0th term, maybe. And so this is kind of what I mean, how I can switch the subscript if it just looks nicer. So S3 would be a plus ar plus ar squared plus ar cubed. And obviously here you're starting to see a pattern. Sn is just going to be your a plus ar plus da, 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 all the way up to ar to the n. This means, notice that if I take r times your Sn, you would get ar plus ar squared plus ar to the n plus 1. Right? So I'm just going to take this and multiply both sides by r. And now what I'm going to do is, what if I take the first equation and subtract the second equation? So if I take 1 minus 2, what I end up with is Sn times 1 minus r is going to be equal to a, and then it's ar minus ar squared minus da da da. Everyone's going to be subtracted except this last one. And so this means I can take my Sn to be a times 1 plus r to the n plus 1 over 1 minus r, and I don't have to worry about dividing by 0 because I'm assuming my r is not 1. And so that is the sequence of partial sums. They all have that form. And so this means I can look at this series to equal the limit as n approaches infinity of this. And notice here, if your r is greater than 1, then we have divergence. Right? Because I'm taking a number that's bigger than 1 and I keep raising it to powers. It becomes an exponential function. Right? And that's going to go off to infinity. However, if your r is less than 1, then you're actually getting smaller and smaller and smaller. It looks like 1 over an exponential function, and then that actually decreases to 1. Decreases to 0, and so if your r is less than 1 in absolute values, then the series is literally, that's going to be 0, so it just becomes a over 1 minus r. And so we can actually find a formula for a geometric series. We can know exactly when it will converge, if your r is less than 1 in absolute values, and when it will diverge, and moreover, I can tell you specifically what the answer is. So that's a very nice series. It's very, very super rare to come across something that you're interested in that will work out nicely like that. But the geometric series does work out nicely like that. So notice that your A and R must be constants. So this applies if the series you're looking at, these guys are constants. It's just one constant times another constant to a power. And you realize that when you're writing it out, the terms look like this. A is going to be your first term, and R is what's called the common ratio, so the guy you keep multiplying by. And it turns out in such a series, if your R is less than 1 in absolute value, it will converge to this. In fact, the convergence here is absolute convergence. You'll notice if I put all my terms in absolute values, it will actually make no difference to the argument, right? Even if I replace all of these guys with absolute values of R, it's still, if the number is less than 1, raising it to a power is going to cause it to decrease, whether it's positive or negative. So the absolute convergence is what we have here. So that's the example of a geometric series. Well, that's the theory behind the geometric series. So that's like the first thing that you see in your table here that I handed out. So let's actually do an example here. We actually did one by constructing it last time. So example, if I look at a series that was, I think we looked at 1 over 2 to the n. The idea is if I give you that, you can realize that, hey, I can write this as 1 times a half to the n. So this means my A is 1, my R would be a half, and this is a convergent geometric series. This means this guy is equal to A over 1 minus R, which is in half, and so that is actually 2. The answer we got was 1 last time, right? I believe. Notice that you kind of have the same argument. I think last time what happened, we started the series at 1. That would not have made much of a difference here. That just means you write it as a half times a half to the n minus 1. And then that applies here as well. And so here your A is equal to a half, your R is equal to a half. And so this would mean the series, if I started at 1, it's A over 1 minus R, and we get 1 that way. So this is me writing the series in this form. That's one little thing you have to look out for. If you're starting at 0, you have to write in the form AR to the n. So that when you plug in 0, A is the first term. If you're starting at 1, you have to write it such that the power is n minus 1. The idea is you want A to be the first term. So if you have to shift the index to make that happen, or do a little algebra to make that happen, that's fine. As long as it follows that pattern, as you start out with a number, and then you keep multiplying that by another number repeatedly and adding all these terms together, it's geometric, and it's going to be the first term divided by 1 minus that number that you keep multiplying by, as long as that number is less than 1 in absolute values. Yeah?
When you said towards the bottom over there equals 1, is that what it converges to?
Yeah, that means if I add up an infinite number of these things, the answer would be 1.
How come the same thing over there converges to 2?
It's not the same thing. Here I'm starting from 0, here I'm starting from 1.
Oh, so it matters where
Which
you
means that this 1, if I'm starting from 0, over here, this is 1 plus a half plus a quarter plus an eighth plus da da da. Whereas this one, if I'm starting from 1, it starts at a half plus a quarter plus an eighth. So this one is adding an extra 1 in the beginning.
Okay.
Right? So where your series is starting, it's important. Like that's telling you, it starts when I plug in n equals 0, plug it into there, that's the first number. And then you realize that, oh, I keep multiplying by a half, that's geometric. So a is my first number, that's 1. And then the number I keep multiplying by is a half, so I divide by 1 minus that number. Here, my first number was a half, so a is a half. And then I keep multiplying by a half, so it's 1 minus that number. I believe this was the example we constructed last time, but if I started from 0, it wouldn't make much of a difference. It's also worth noting, and we'll speak about series that have this form in general. They're called alternating series, but let's say I had something like this. This is called an alternating series because that minus 1 to the n will switch alternate signs, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. But as far as you recognize it as a geometric series, that actually doesn't matter. In other contexts it might. You just need to realize that this is the same as 1 times minus 1/2. And that is still less than 1 in absolute value, so it does converge. And so it would still, in this case, the series would converge to a over 1 minus a half. So that would be 1 over, that's 3/2, so that would actually converge to 2/3. And that series, if you start plugging in the numbers, that's actually 1 minus a half plus a quarter minus an eighth plus a 16 minus the signs alternate here. So you'll expect to get less than the answer that you got here, which in fact we did. That will actually add up to 2/3. But all of these, the example of all of these are geometric, they fit this pattern. They fit this pattern. So that's one thing you can look out for. Series, that's a very nice series. We can have absolute convergence and we know exactly what it will converge to. Very rare, but for a geometric series that actually works out. Here's another example. 1 plus e to the n over 4 to the n plus 1. Now, we have a lot of examples to get through, so I'm just going to jump into it. You'll have plenty of practicing recognizing forms when you actually do the homework, but I'm actually going to just show you how you'd sort of look at that. So you see something like that on a test. And it's kind of like the same idea as integrals. There's a form you want to look for, sort of like you want to look for something like, oh, would substitution work? It's the same kind of deal. So when you start seeing things raised to powers, geometric series is one of the things you're going to start thinking about from the beginning. So you're always going to see, can I simplify this to look like a geometric series? Or do I have to do something like the root test? The root test is also something where things raised to the nth power would be a useful thing to look at. Notice here, one thing you can do is you can split the fraction. And from Calc 1, we know that the sum of the series of a sum is the sum of the series. So this is going to be, sometimes I might get lazy and just write 0 here to be understood. This I can look at as a quarter times a quarter to the n. This guy I can look at as a quarter times e over 4 to the n. Notice that in here, a quarter is less than 1, and also e divided by 4 is less than 1, because e is 2.7128, blah, blah, blah. So these are both geometric and they both converge to A over 1 minus R. And this again, A over 1 minus R. So this converges. In fact, it converges absolutely if you had to specify that. Right. So in series, mostly you're going to be doing is algebra. You're going to be simplifying things to kind of get them to force them into one of these forms in the table to take advantage of. We'll use calculus every now and then, but predominantly it's going to be an algebra kind of thing. So you kind of want to force things into a certain form that you know how to do. Yeah.
Sorry, when you put less than 1 right there, are you just specifying that that's always going to be less than 1?
That's the quarter. And this is less than 1. Because that's the condition for convergence. The thing raised to the nth power must be less than 1 for it to converge.
Okay.
If it were greater than 1, my answer would be it diverges.
Okay.
So the answer would be infinity diverges.
Okay.
But if it's less than 1 in absolute value, then raising it to the nth power means decreasing. In fact, it's decreasing so fast that eventually it's like you're adding nothing because the terms are so small. They're theoretically 0.
Okay.
Yeah.
How do you test if it converges absolutely?
Converges absolutely means, remember this converges absolutely means if I just put absolute values around each term, it converges. And in this case, if I put absolute values around these guys, it wouldn't actually make a difference because it's already positive even. So the absolute value of the quarter won't matter. Technically, if I put the absolute value around this, it would be less than or equal to that, but you'd still get convergence using something we call the comparison test. Yeah. So absolute convergence literally means put absolute values around each of the term and then do a test to see if it converges still. In the geometric series, we don't actually care about the signs. Like once our magnitude is manageable, once our magnitude is less than 1, that's all we care about. The signs actually don't affect it. We spoke about the divergence test last time, so that's the kth term test. That's the second thing in our table. So the next one is the integral test. That's what I'm going to talk about. And by the way, the table is very useful that I gave you because it also gives you hints about when you might want to use this guy, right? So notice here in the integral test, it's like you have a series. You can think of the formula given as a function, and that function is continuous and decreasing and positive. And of course, it should be something that's very easy for you to integrate. This is the integral test. This really shows up in 11.3, I think. So let's say you have this series from, almost doesn't matter where it starts from, of an. But we can consider an as some function of n where f is continuous, decreasing, and it's positive everywhere. Which means your function, it might not look like this, but it has to have something like this, right? It has to be going down as you move from left to right. So here's the idea. When you're doing a series, right, you only care about the integer values, right? So it's like you're just adding up this number, right? You can imagine like a rectangle erected that has width 1, and so adding that number is like finding the area of that rectangle. So the series really only works on the integers. For instance, where the series adds up. But if you were to consider the integral of, say, the f of x, what would that compute? that will compute literally everything. It would even fill in all the gaps. So basically the idea is, if you have the sum of a function, it's always going to, and it has these properties, it's always going to be less than the value that the integral of the function gives you. Because the integral is going to fill in gaps that this guy doesn't even touch. Because the integral literally works on all real numbers in the interval, whereas the series is only going to be adding up the values of the function that happen on the integer values. So essentially what you have, this sort of implies, and I'm skipping a lot of the theory here, this sort of implies that the sum of this guy will always be less than or equal to the sum of this guy, the integral. So if I start from, say, 0 to infinity, the integral from 0 to infinity is going to be larger. And so the thing is, if this improper integral converges, it's forcing this one to converge, right? Using the comparison test, right? If I can actually compute this integral and it stops at some finite positive number, then this series has to stop at some finite positive number. It can't go off to infinity. And guaranteeing that these guys are always positive means that there's a 0 on this side, so it can't push back down to negative infinity either, right? So that gives you sort of the integral test. So the integral test says, under these conditions, so basically the integral test implies that under these conditions, if the integral converges, and this is an improper integral now, so you're going to have to use the theory for the improper integrals, then the series will converge. Yeah.
If the integral if the integral diverges, that doesn't necessarily mean that the series diverges, right? Because like it's so much more.
Yeah, because it's a lot.
Okay.
I mean, there are theorems about that. I think it works the other way. I forgot if it works the other way. It definitely works that way. I don't think it's an if and only if. Oh no, they both work together. And you can see that from the table. But you can't say that from here. It's an extra thing that you'd have to prove.
Okay.
Right? So you can think of it as an if and only if. This guy converges if and only if that guy converges. So if this diverges, you can assume that this series also diverges. But that's not straightforward from the comparison test. It takes a lot more, there's a lot more background to that.
Okay.
But the idea is of course, we want the f of x to be easy to integrate. Right? If you're running away from a hard series problem and you just run into a hard integral problem, I don't know how much benefit that would be to you. So the idea is, as a series, I don't know how to deal with it, but if I just think of it as an integral, hey, I actually know how to integrate that, and then this becomes a thing you can use. So one situation in which you want to use the integral test, first you have to verify that these conditions hold. Right? It's continuous, it's decreasing, it's positive. And then you can say, oh, but that thing looks like something like I know how to integrate very easily. You can do the integral test. Yeah.
But it only has to be continuous. Well, it only has to meet those criteria for n or x greater than 0, right? Because we don't care if it.
Well, the start point kind of go hand in hand. So you can start these guys from any point you want in theory.
Okay.
Yeah.
But so, for example, because you said that that's common, like going from 0 to infinity is common for series.
Yeah.
So, for example, like if you had, the series of 1 over n, right? So if you made that into a function, it would be discontinuous at 0, but you only care about, if you had n equals 1 to infinity, it wouldn't.
Yeah, but the series itself, you're looking at 1 over n, you couldn't start from n equals 0 anyway, you'd start from n equals 1.
Right. So
And then what you would look at is the integral from 1 to infinity.
Okay.
You'd start the integral at 1 as well.
Why is it important that we're not that were greater than 0?
Because we want to maintain that we're bigger than 0. We don't want to end up in a situation where we're adding a bunch of negative terms that accumulate to infinity and it goes that way.
Okay.
And the integral, we can't really account for that.
Okay. Great.
It's just a control, right? Let's just look at it all positives. There's no ambiguities. We're erecting rectangles. They're all above. They're all giving us a positive error. We know how to deal with that very nicely.
Could we make everything negative? Or is it just a problem if it's a mix?
If it's a mix, it gets difficult.
But if you made everything negative, you can sort of just flip the sign.
Yeah, you can just, yeah. You can, yeah, because that would be a property of series and integrals. Like if the terms are all like negative here, or after some point they're all negative,
Right.
you can just split the series in two and then factor out the negative from that side, use the integral test, and then it's just the negative of that. Yeah. But it's a nice test if what you're looking at is something that's easily integrable and it fits this criteria. So let's look at some examples for that. So here's an example that it looks crazy when you first see it. Like you see something like this, n equals 1 to infinity of e to the 1 over n squared. You know, what is that? Right? So 1, the limit does go to 0, so I can't immediately say it diverges. 2, it's not a geometric series because the base is not a constant. Right? It's not telescoping, right? Because these are going to all be positive numbers, so if I wrote out the sums, no one's going to kill each other. They're not going to cancel out. So now I'm kind of stuck, like, well, that's really weird. So far, I do not know how to deal with this. And so one thing you might notice, because again, there's sort of an order in which you think of things, just like with integrals. You first like, does the power rule work? No. Does substitution work? No. Does this work? So you'll run through quickly a bunch of things in your head, which you, with experience, you'll be able to tighten down which ones you look at first or second. And then you'd realize you get to what we've done so far is not going to work on this. But then you kind of realize, hey, if I took the derivative of 1 over x, that's actually minus 1 over x squared. So this guy here, notice that this function n is positive, it's decreasing, and it's continuous. And if I do the integral from 1 to infinity of e to the 1 over x squared, I actually know how to integrate that by just setting u equals 1 over x. My du would give me minus 1 over x squared dx. So minus du is that 1 over x squared dx. And so this guy really just becomes the integral as x goes from 1 to infinity of e to the u du. And that is equal to just, of course, e to the u from x equals 1 to infinity, and that is just going to be e to the 1 over x between 1 and infinity. And yes, technically you're supposed to write limit as n approaches infinity from 1 to n and blah blah blah, but you sort of get the idea. You're going to plug in e to the 1 over infinity minus e to the 1 over 1. Right? 1 over infinity. Right? I mean, yes, technically speaking, and I guess since we're in Cal 2, we should sort of. Technically speaking, that's how you would interpret it. But was this go to infinity, that goes to 0, so that goes to 1 minus e. To n. Let's plug these in. So if I plug in n, I get this, minus plug in 1, I get that. And so the upshot is that's a number converges. And you can say by the integral test. You should always state what test you're using. So a good answer would show that you check the conditions necessary for the test to work, you perform the test, and then you can make a conclusion based on the test. So as a series that was very complicated, but as an integral it wasn't. And as an integral it converged. Next guy on the list is a p-series. These guys are called p-series. These series have the form one over n to the p. Recall, the integral from 1 to infinity of 1 over x to the p converges if, we had a theory about that. If p is greater than 1, and diverges otherwise. So, by the integral test, I know that the series from 1 to infinity of 1 over n to the p converges if the p is greater than 1 and diverges otherwise. So let's look at some examples. First example, n goes from 1 to infinity of 1 over n. Here, p equals 1. This means this series diverges. By the way, this is a very famous series. It's called the harmonic series. It's very important. It often shows up in various contexts, so we've studied it a lot. And there are tons of ways to show that it diverges, but you can use the p-series test to show that it diverges. You can use the integral test to show that it diverges. Because the p-series test is really just an application of the integral test, but it's just something that you can quickly just know. You don't have to go through the integral. You know it's going to work out the way it does. Another example, if you look at the series of 1 over n squared, you can immediately say this converges by the p-series test. Literally just looking at that form. Now, very rarely are you going to be given a series that's this simple, but the idea is you can be given series where you can kind of approximate them using these guys and use that to make a conclusion about the other series. Sort of like how there was a comparison test for improper integrals, right? So I can use an integral that I know about to approximate an integral I don't know about, and if the relationship in the inequalities works out a certain way, I can talk about the convergence of the one I don't know about with the other one. So that sort of tells me if I can show that there's a series that's always less than or equal to this, and positive, it has to converge, right? If I can show that there's a series greater than or equal to this one, then it has to diverge, right? So you can do that as well. But that's the p-series test, so it's a nice thing to use. And speaking of what I just spoke about, the comparison test is going to be the next one. So again, notice I didn't tell you what this answer was. I just know it converges. It has to converge because the integral is going to converge. And the integral is going to be bigger than whatever this answer is. Did I write that down? Oh, food for thought. It's actually pi over 6. Pi squared over 6. Obvious, really, but yeah, turns out that's pi over 6. I really should have that memorized. I never remember these things. Yeah, so if you add 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus da 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 forever, it ends up being pi over 6. Pi squared over 6. That's a topic for another class. So there's the comparison test. This is if you know that an is less than or equal to bn term by term, then you can clearly see that if I add up all those terms, it's going to be less than the sum of those terms. And therefore, similar to the comparison theorem for integrals, the same idea holds here. If the series Bn converges, then An must converge. Right? If the bigger guy stops at a number, the smaller guy can't pass it. It has to stop at a number as well. Also, if you know information about the smaller one and it diverges, then the larger one must diverge. Right? I want you to realize that no info from this test in the other cases. Meaning, if the bigger one diverges, I can literally say nothing about the smaller one based on this test. It could converge, it could also diverge, but it's just less than that one. We don't know if it gives us a finite answer or it also gives us an infinity that's a smaller infinity. So you wouldn't be able to tell. As well as if the smaller one converges, then the bigger one could converge or it could diverge. You won't have any information. But in these two situations, you know for sure. If this one adds up to a finite number, that one also has to add up to a finite number. If this one adds up to infinity, this one is greater than or equal to that, it also has to add up to some infinity. So the comparison test is really useful if you know about one series, whether it converges or not, and you can make this sort of relationship with a series that you don't know, and you can apply one of these. So let's actually look at some examples there. And I think that's as far as we'll get here. We'll talk about the rest next time. The limit comparison test is really nice because we don't actually need to know the inequality relationship, which is not always going to be clear. But let's use the comparison test on this example. Series. N goes from 0 to infinity of 3k divided by the square root of 2k to the 5th plus 2k plus 1. Now you look at that, not geometric. It's not going to be, what we call it, telescoping. It's not a p-series. I don't think that's going to integrate very nicely. It's going to be hell to integrate. So then you kind of start thinking about, well, the intuition that you get from limits can often apply here. So you start thinking, well, you know, as we're going off to infinity, the smaller guys don't really matter. I can sort of ignore them. And when I ignore them, I can sort of think of this guy as a p-series. So let me actually, instead of looking at it as a whole, let me kind of block some information that's not really as important and look at it as a p-series. And so now the idea is, can I approximate that with a p-series in such a way that I know how the inequalities line up? And so note here, if I take 3k over this guy, k to the fifth. I just changed the variable here because I don't want you guys to get used to a certain variable. You can use anything you want. Okay. Notice that this has to be less than or equal to this. Less than or equal to this. Since denominator is smaller. Right? Divide by a smaller number, you get a bigger fraction. Right? So I definitely know that that's the relationship. Right? I literally subtracted things from the denominator became smaller, so the overall fraction got bigger. And this guy is equal to 3 over radical 2 times k over k to the 5 over 2. So in other words, this is 3 over radical 2 times 1 over k to the, what would that be? 3 halves. So what that in fact tells me is that, let me call this s. That in fact tells me that my s is less than or equal to the sum of this guy. But this guy is a convergent p-series. Therefore, this implies S converges by the comparison test. So this is where p-series are coming useful, right? They're very trivial to look at on their own. You'll never get a question where, oh, this is just a p-series. It really comes when you have something really complicated that you want to approximate using a p-series, because it's easy to know about the answer in the p-series form. And so here, this is definitely less than or equal to that. So it means that the series is less than or equal to that series, and this one I know converges, so the comparison test tells me that this also must converge. So the idea is, if you have something like this, or any rational function, if you kind of block out all the lower powers and realize that when you simplify, you get a convergent p-series, it might converge. The only issue that might arise is you might not know which way the inequality turns. That might be an issue. In this case, I was sure because the denominator got smaller, but it could be the case that I had things in the numerator that I also had to subtract. And so that would make the fraction smaller. So now I'm like, I made it smaller, but then I made it bigger. I don't know who's going to win. And you won't always know which way the inequality turns. And that's when something like the limit comparison test comes in useful, which is the next test we'll talk about. Because it doesn't require you to know how the inequality is on it. So we'll stop there. Do the rest of the test next time.